Okay, let's go. So the last 4 days we've been discussing volumes of revolution, right? And we have two techniques, the disk method and the washer method, to compute the volume of those specific types of solids. Okay. Today we're going to look at the third and final method, and it's different in a couple of ways, but it's similar in other ways. All of the problems that we're going to do are called volumes that are formed by perpendicular cross sections. Okay, and they are not volumes of revolution. Okay. So make sure you see that up front. There are not volumes of revolution. So we're not revolving. We're not doing the pineapple. Okay? These are formed in a different way. And it might take just a little bit to try to figure out what's going on here. So, rectangles, rectanges. It's like an orange. There. Yeah. It's the only thing that rhymes with orange. Rectorange. And so we're going to do these different shapes, okay, knowing that on the AP exam they could throw you a shape that's different than any of the ones that we do. Okay, but we're going to get down the basis for how to solve any problem by how to set it up and then how to compute the volume. So let's take a look at this picture here. This is an introductory picture of the kind of volume that is formed through a perpendicular cross-section. And what happens is this is the base right here. The circle is the base. Okay? And then rising up from the base is a square. Okay? In other words, the square is perpendicular to the base, okay? And it's perpendicular to this axis right here. That's where the right angle comes in, okay? Now, the fascinating part about these is that there's not just a single rectangle, but there are multiple, not just a single square, but there is a square for every one of the x values along this axis. Okay, so what happens is we end up having squares that go everywhere along this axis right here. We'll call this the x-axis. And the size of the square varies based upon the value of the x. So, if you can see what I'm doing here, this would be the square that would be formed based upon this x value. And so the shape is actually really weird because we go across, here's my length, that determines the side of my square. And then the square gets built from there. Can you start to see it? Okay, now I'm going to show you a different image that shows all of the different shapes in a different format. I'm going to zoom in on this. Oops. Okay, so maybe hit the light because it might be easier to see on this one. Okay, so here's how you have to see this. So the paper here is what we've been doing all along, and the base here, the area. Remember how he always says you must identify the area. And so the area is this region right here. It's on the flat paper. But rising up from that are these rectangles. And the size of the rectangle is based upon the distance between when we do top minus bottom all the time for the area between two curves. This is the distance between here and here, here and here. That determines the height of the rectangle or the square or the semicircle or whatever. Okay? So what this person did, which is really clever, is they took the same exact region, okay, and then made different shapes. So it's y equals x squared, okay, picture this on your paper, and then y equals 0 right here. And then they made semicircles that projected out from that. And so the shapes, you can see they're certainly not volumes of revolution. They're kind of like these weird shapes that can form by accumulating all of the shapes that we have and accumulating all of them. So it's kind of like a Riemann sum, but I want you to imagine us taking this shape and then we put it in the egg slicer, and then these are all the different shapes that come out. And every shape that comes out is either a square or a semicircle or a triangle or a rectangle or anything like that. Okay? So what we're going to do is we're going to do the whole gamut of all of these on the same function, same area, and we're going to draw our pictures and we're going to try to figure out how to find the volume of these. Okay, hit all the lights again. And I think instead of doing practice runs, we'll get enough practice by going right to our problem. So here is our problem. I think I might make that. Yeah, that's a little bit better. Okay, so in your notebook, in a brand new section, here's what I want you to do. Let's identify two functions. One is f of x, and it's the line. So it's 0.5x plus 1. And then the red function is a parabola. It's g of x, and it's equal to negative 0.1x squared. And we're going to do these, we're going to do all of these from 0 to 4. Okay? So 0 to 4. And we're going to do each of these shapes one at a time. Okay? So go ahead and draw the picture on your paper. See the parabola just kind of comes down here, and the line goes up here. And then we'll draw the pictures. So the first thing I want you to do is lightly shade the flat region, just like we always do. Lightly shade this. I wish I had a shade. That's what they come up with, a shade marker. Be like a felt row. Just kind of sweep over it. The cap would be really long. You know what I'm saying? You could just kind of sweep over it. I should invent that. So with that region shaded, we're going to do the squares first. Okay? So here's what we're going to do. We're going to draw the squares. Now, this is really hard because we have to have them appear that they're projected, that they're coming out. In fact, I have a very sophisticated prop here to demonstrate the squares coming out. And so the squares, the square would not be fit right here. This would be a bad fit for this square. This would be a bad fit for the square. This square has to come straight out when the distance between the top function and the bottom function are exactly the distance that for this particular square. See? Bad, bad, good, right here. Okay? So the distance on mine, I'm going to draw this down here. Okay? Right there. And then in order to try to show that this is being projected up, I'm going to do a little angle thing here where I'm going to go up, and then I'm going to go parallel here, and then I'm going to come down. So you got to use your 3D brain to see that square coming out at you. It looks like this if we could hold it in our hands. Okay, so let's do the other ones the same. So I always like to do the end ones. So the one on the end would go here, and then it'd be this is the biggest rectangle, or the biggest square, I mean. That's the square that's projecting out, and it's the one on the end. If you ever took an art class and you talk about perspective, this is like all part of that. And then let's do the smallest square. The smallest square would come like this, like that. Can you see them sticking out at you? It's kind of, the more you do, you got to picture that picture that I just showed you where they're all just, there's a whole row of them. Okay? All right, now here's our problem. How do we find the volume? Oh, and you can do this now. You can connect the dots on the end if you want to. And this one is kind of a weird one here. And if you kind of look at, if you stare at it, that's going to represent all of them now. It's the full solid. You know what I'm saying? So now if I held this in my hands now, I would be able to hold all of them at once, and it's all of these squares. Okay, so here we go. How do we find the volume of this? Well, I'm going to teach you a technique that is a little bit unorthodox at first, but because mathematically it's not correct, but it will help you, I think, to see it. So the first one is the squares. Okay? So the way that I look at it, I say, okay, to find the volume, I want to integrate squares. And that's the part that's not really mathematically proper. Okay? But it gets you the sense that we're going to accumulate an infinite number of squares. Okay? So for this particular problem, we're going to go from 0 to 4 because the first square is at 0 and the last square is at x equals 4. So x equals 0 to x equals 4, and we're going to accumulate an infinite number in between those two because that's what the integral can do. Now, right here, though, this is where we have to have the formula for a square. Okay? Using f of x and g of x. Okay? this is where that has to go. So I don't know about you, but I think of this, I think, all right, every one of these squares right here, the area of a square is you take this side and you multiply it by this side, and the area is side squared. That's the area. So what I'm going to do is I'm going to put in s squared. Because that's what I know is the formula for a square. You multiply the side times the side and you get the area. Okay. Now, the deal is, though, we just need to know what s is. So in this problem, what is the distance s at any given time? F of x minus g of x. Because we're doing top minus bottom. And when we do that, this is s. All the time for any given x value. So we say s is equal to f of x minus g of x. Okay? Now, this is correct. The only thing that we need now is dx. So what does the role that dx plays? Well, a square, okay, geometrically, a square has no depth. There's no thickness to a square. Okay? So we actually have to have a width here, and that minor width represents the fact that instead of having an actual square here, what we actually have is it's got a thickness here. Okay? And the thickness of this thing is dx. Okay? Think of it as like a rectangular prism. It's actually length times width times height. And the width of that thing is dx. Okay? All right. Go to your calculator right now. Put in your f of x and your g of x. And then find the integral. Let's use y3 as our s. And we're going to use the same functions for all of them, just so we don't have to retype those in. So, and I'm just going to zoom. I'm just going to graph this one and just make sure we're doing the right thing. And that looks good. So let's do the integral. Oh, let's do y3. y3 is going to be y1 minus y2. And you don't technically have to do this, but it makes computing the integral a lot more manageable if you want to modify it. You get 30.048. Okay. So, the integral, you could also write this as the integral from 0 to 4 of f of x minus g of x, quantity squared. Okay? That's perfectly acceptable on the AP exam. this is acceptable. And then, of course, you could write the whole functions out, but if you make a mistake on it on the exam, then you get that you don't get credit for it. So I suggest reusing those. Okay. We're not getting the same answers? 0.5x plus 1, negative 0.1x squared, y1 minus y2. Okay, sweet. All right, let's move on. So that was squares. Now let's do semicircles. Okay, so redraw the whole thing. And now we're going to do semicircles. Okay, now drawing the semicircles, we have to imagine a semicircle projecting out from this. So I have to find the right place to put this specific one. And so this one looks like about right here is where it belongs. Because notice the distance between the diameter of the semicircle has to match the diameter as the distance between those two. Okay, so right here, whoa, vaporized. This is coming down here. Okay, and then now we have to draw a semicircle. So this thing is projecting out. So it's going to look something like this. So I always recommend doing somewhere in the middle, and then do both of the endpoints. So there's one, and there's another one. Can you see it? And then actually, if you were to put a dot on the top of each one of these, and if you draw a line between those, that's actually the thing that would contain it. If this was like a tent, then that would be the bar that goes across the top of the tent. You know what I'm saying? So you could draw all of them in there, and this would be what it would look like. You see a teepee? It's half an ice cream cone. Okay. So let's follow the technique. Okay, so I'm teaching you a technique that I'd like you to follow if you find it useful. The volume here means that we're going to integrate semicircles. Okay, none of that is mathematically proper.
What if we were to write down the AP test?
They'll ignore it.
Okay.
Yeah. Okay. So By identifying that, you're identifying what shape you're using, and then it lets you know that's the formula that you need. So I need the formula for the area of a semicircle. It would be 1/2 pi r squared. Okay, so watch this. We're going to go the integral from 0 to 4 of 1/2 pi r squared, and I'm going to put the dx in there. Okay. The dx, again, remember, is the width of this slice. This slice cannot have no dimension. It has to have a dimension, a width. And dx represents that width. Okay? Okay, well, look at this. We have everything that we need, except we don't know what r is. If only we could find out what r is, we would get this. That's right. F of x minus g of x divided by 2. Because the radius is only half of this. So we're going to do r is equal to 1/2 of f of x minus g of x. Okay. All right, reach for your calculator, and now you have everything you need to do it. But I'm going to modify y3. I modified y3, so it's y1 minus y2 divided by 2.
Why is that 1/2 there again? 1/2 f(x) minus
Because the total distance from here to here is f of x minus g of x. But that's the diameter. And for the formula, we need the radius. So we just take that and divide it by 2. Okay? y3 squared .5 pi. $11.7998. Anybody else get that? Is that right? So I put the 1/2 pi in the front. 0.5 pi, that's the 1/2 pi. Radius was my y3 squared. Yes. I modified y3. I did this. If you put it in there, if you brought it out, it would be 1/4. And then 1/4 times 1/2, it would actually be 1/8. If it's the same as pi r squared divided by 8 if you drop the half. So far, so good? Okie doke. All right, erase or move on to the next one. Let's redraw. Yes. Yeah, they would provide you with the area. All right. Where height is half of base. Okay. This time we're projecting out rectangles where the height of the rectangle is half of the base. And the base, this would be these are represent the base. They'd be long and short. Okay? I don't have a rectangle. Can't do the problem. Yeah. 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 No, but I'm showing you how you come up with them. The ones that are the trickiest, like this one, this one and the last one, the fifth one, that's extra funky, which is kind of fun.
If they gave us a question on the AP exam like this, would they tell us use semicircles or would they?
Yeah. Yeah. They would
So if
set it up by telling you what you have to do. All right. This time, I'm going to come down this time rather than going up. Changing it up. So now, these are not squares. They're rectangles. And the dimensions on the rectangles are such that whatever this is double it. Or vice versa. Okay? All right, so what does this mean? So it's shorter than the square if it were squares. It's flatter, shorter than if you had squares. Okay. Rectangles where the height is half the base, so we're going to accumulate a whole mess of rectangles. Okay. So this is the integral from 0 to 4. I don't know about you, but I know the rectangle formula is length times width. Right? Length times width. If only we knew what length was and then what width was, we would have it made. So I guess we should establish what's length and what's width. Who should length be? Yeah, this. Let's make this one be length. If that one's length, then this one is width. Okay. So, what is length? Look at that again. Length is f of x minus g of x. because it's the distance between these two. And for any given x value, this is kind of the key thing, for every single x value, the length changes. Take the f of x value minus the g of x value. Okay, what's the width? Divided by 2. So you can write it any way that you want to. Some of you might like writing it like this. Okay, that's the same as saying like I did 1/2. Same thing. But I spy something here. This might be easier to write instead of length times width. You got to multiply those two, right? So what do you get? F of x minus g of x squared divided by 2. See that? Length times width is this one times this one, and that's where we get that one. Does that make sense? Length times width, multiply these two together, it's f of x minus g of x squared divided by 2. This is pretty easy, isn't it? You just got to identify the formula. Then you got to know how to get there with your f of x minus g of x or whatever. Okay? All right, did anybody get an answer for this one? $15.02 with nothing after it?
Nothing after it.
Okay. So make sure you get this answer for that one. Okay. The last one we're going to do is going to be a mind stretcher. Okay? Because we're going to do a rectangle with a function for the height. We're going to skip the equilateral triangle for now, because you guys were getting it. Rectangle with a function for a height. Okay? The function that we're going to use is the sine of x. Now, we're not going to finish this one here, but let's try to draw it, because this one is weird looking. We might have to look at this from multiple perspectives. So this is a rectangle with a height of y equals the sine of x. Now stop and think what's being asked here. So it's still a rectangle. Okay. Well, actually, that's a bad one for that one. That one's got a height of 0. Can anybody picture what this looks like? Okay. What does it look like?
If you look at the side, the height of it is this.
Yeah. If you took this and now you looked at it from eye level, this is bad right here. Maybe I shouldn't use sine of x. the height of the rectangle is determined by the sine function. Yeah, we're gonna have to redo that one so it's not sine of x, because we don't want it to go.
Or absolute value.
We can do absolute value of the sine. That's good, because then it's going to do this. Okay. All right, we'll finish that tomorrow then. Make sure you're all. Oh, Mrs. Johnson needs to know how many people are coming.